Tonight, we're going to talk about something that happened billions of miles from Earth, in a region so cold, so dark, and so utterly removed from human experience that for most of history, we didn't even know it existed. A small spacecraft, no bigger than a grand piano, sailed past Pluto in July of 2015 and gave us our first close-up look at a world that had been nothing more than a fuzzy dot for nearly a century. That moment, when New Horizons skimmed past the dwarf planet at over 30,000 miles per hour, was supposed to be the climax of the mission, the grand finale. The reason NASA had spent nearly $1 billion and almost a decade getting that spacecraft to the edge of the solar system. But what nobody fully appreciated at the time, what most of the public still doesn't understand, is that the Pluto flyby was just the beginning. The real mystery, the strange and unsettling discoveries, the data that scientists are still struggling to explain, all of that came after Pluto. In the years following that flyby, New Horizons pushed deeper into a region of space we've barely begun to map, and what it found out there has raised more questions than answers. And by the end of tonight, you're going to understand why some of what New Horizons has seen past Pluto has never been fully shared with the public, why certain images and data sets remain buried in technical papers that almost no one reads, and why the further this spacecraft travels into the dark, the stranger the universe seems to become. Before we get started, if you love exploring the unknown corners of our solar system as much as we do, take a second to like the video or subscribe. It's a small action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why what New Horizons saw past Pluto matters so much, you have to understand where it is and where it's going. The spacecraft was launched in January of 2006 from Cape Canaveral, riding atop an Atlas V rocket. It was the fastest spacecraft ever launched at that time, leaving Earth at roughly 36,000 miles per hour. To put that in perspective, the Apollo missions took about 3 days to reach the Moon. New Horizons crossed the Moon's orbit in just 9 hours. That kind of speed was necessary because the destination was so far away. Pluto, at the time of the flyby in 2015, was about 3 billion miles from Earth. Light from the Sun, traveling at 300,000 kilometers per second, takes more than 4 hours to reach Pluto. Radio signals from the spacecraft, traveling at that same speed, took just as long to reach mission control, which means that during the actual flyby, the team at the Johns Hopkins Applied Physics Laboratory in Maryland couldn't control the spacecraft in real time. They had to program it weeks in advance, send the commands, and then wait. If something went wrong, they wouldn't know about it for hours, and by the time they found out, it would be far too late to do anything about it. But nothing went wrong. The flyby was a stunning success. New Horizons captured images of Pluto and its largest moon, Charon, that revolutionized our understanding of the outer solar system. We saw heart-shaped plains of frozen nitrogen. We saw mountains of water ice taller than the Rockies. We saw evidence of glaciers, of possible cryovolcanoes, of an atmosphere far more complex than anyone had predicted. Pluto, which had been demoted from planetary status just 9 years earlier in a controversial decision by the International Astronomical Union, suddenly seemed more alive and more dynamic than many of the official planets. The public was captivated. For weeks, Pluto's heart-shaped feature, officially named Tombaugh Regio after Clyde Tombaugh, who discovered Pluto in 1930, was on the cover of newspapers and magazines around the world. NASA had pulled off another triumph. And then, in the public consciousness at least, the story essentially ended. But for the team running New Horizons, the story was just getting started. Because the spacecraft didn't stop at Pluto. It couldn't stop. It was moving far too fast, with no way to slow down. There were no rockets capable of putting it into orbit around the dwarf planet. The mission was designed as a flyby from the very beginning. So after the closest approach, New Horizons just kept going, sailing deeper into a region of space called the Kuiper Belt. And here's where things start to get strange. The Kuiper Belt is one of the most mysterious regions in our solar system. It's a vast disk of icy bodies that extends from the orbit of Neptune out to about 50 astronomical units from the Sun, which is roughly 50 times the distance between Earth and the Sun. It's sometimes compared to the asteroid belt between Mars and Jupiter, but that comparison is misleading. The Kuiper belt is much larger, far more massive, and contains objects of much greater variety. Pluto itself is just one of many Kuiper belt objects, and not even the largest one. There are believed to be hundreds of thousands of objects out there larger than 100 kilometers across, and possibly trillions of smaller ones. We've only directly observed a tiny fraction of them. Most of what we know about the Kuiper belt comes from theoretical models, from indirect observations, and from the handful of objects that have been studied in any detail. And until New Horizons came along, no spacecraft had ever visited any of them. After the Pluto flyby, the mission team made a decision that would prove to be one of the most consequential choices in the history of planetary exploration. They had fuel left. They had a healthy spacecraft. They had instruments still working perfectly. And they had the political and scientific will to keep going. So they petitioned NASA for an extended mission. They wanted to target a second Kuiper belt object, something even further out than Pluto, something that no human eye had ever clearly seen. The challenge was finding a suitable target. Kuiper belt objects are small, dim, and incredibly far away. They're almost impossible to detect from Earth. And whatever target they chose had to be along the trajectory the spacecraft was already on, because New Horizons had very limited fuel for course corrections. They couldn't just pick any object. It had to be something the spacecraft could reach without burning through its remaining propellant. After years of searching, using the Hubble Space Telescope to scan the region of space ahead of New Horizons, the team identified a candidate. They called it 2014 Mu-69, and it was orbiting the Sun at a distance of about 44 astronomical units, roughly 1 billion miles past Pluto. It was small, possibly only 20 miles across, and at that distance from the Sun, it received only a fraction of the sunlight that Pluto receives, which is itself only a fraction of what Earth receives. The temperature out there hovers near absolute zero. The Sun, from Mu-69's perspective, looks like just another bright star in the sky. There's no warmth, no weather, no atmosphere worth mentioning. It's about as close to the empty void as you can get while still being inside the solar system. The target was eventually given a nickname, Ultima Thule, a term from medieval literature meaning a place beyond the known world. Later, after some controversy over the historical use of that name, it was officially renamed Arakoth, a word from the Powhatan language meaning sky. But regardless of what you call it, when New Horizons reached this object on January 1, 2019, 3.5 years after the Pluto flyby, it became the most distant object ever visited by a human-made spacecraft. And what it saw there was, in some ways, even stranger than what it had seen at Pluto. The first images of Arakoth showed something nobody had quite expected. The object wasn't a simple sphere or an elongated potato shape like many asteroids. It was two distinct lobes joined together at a narrow neck, like a snowman or a peanut. Astronomers call this a contact binary, two separate objects that came together so gently billions of years ago that they merged without destroying each other. And the way they came together, the angle, the orientation, the lack of damage at the contact point, all suggested something profound about how planets and planetesimals form in the early solar system. The collision happened at almost walking speed, just a few miles per hour, like two snowflakes drifting together rather than two rocks slamming into each other. This single observation rewrote textbook understanding of planetary accretion. The dominant models of how solar systems form had predicted much more violent encounters during the early days of accretion. Arakoth suggested something gentler, something more like a delicate cosmic dance. But that wasn't the only surprise. The surface of Arakoth was redder than scientists had expected, a deep reddish-brown hue that suggested complex organic chemistry. Out there, in the absolute darkness and the absolute cold, molecules called tholins, complex hydrocarbons formed by cosmic radiation interacting with simpler ices, coat the surface in a thin layer of reddish material. These tholins are the same kind of compounds found on Titan, Saturn's largest moon, and they're considered some of the building blocks that could lead to life under the right conditions. Finding them in such abundance on an object so far from the sun suggested that the outer solar system might be rich in organic chemistry in ways we hadn't fully appreciated. The very ingredients of life, or at least the precursors to those ingredients, are scattered throughout the Kuiper belt, sitting frozen on the surfaces of objects we've barely begun to catalogue. The Arakoth flyby lasted only minutes. New Horizons was moving so fast that the close encounter was over almost as soon as it began. But in those minutes, the spacecraft captured gigabytes of data, far more than could be transmitted back to Earth quickly. The bandwidth from a spacecraft that distant is severely limited. Radio signals weaken with distance, and the data rate from New Horizons is measured in kilobits per second, comparable to a dial-up modem from the 1990s. Transmitting all the data from the Arakoth flyby took more than a year, and during that year, as the data trickled back, the mission team began to notice things in the images that didn't quite fit. Anomalies, patterns, features that raised questions they hadn't expected to be asking. The anomalies began with the shape itself. When the first detailed images of Arakoth came back, scientists immediately noticed that the two lobes weren't quite the spheres they initially appeared to be. The larger lobe, nicknamed Ultima, was actually flattened, like a pancake or a slightly squashed disc. The smaller lobe, called Thule, was rounder but also somewhat compressed. Nothing in our understanding of how objects form in the outer solar system predicted this. The standard models suggested that objects accreting from dust and ice in the early solar system should form rough spheres, gradually becoming more spherical as they grow. Flattened shapes are extremely difficult to explain. They would require some kind of rotational dynamics or thermal process that we hadn't accounted for in our theories. And remember, Arakoth has been sitting out there essentially untouched for 4.5 billion years. It's a relic from the dawn of the solar system, preserved in the cosmic deep freeze. Whatever forces shaped it operated very early in solar system history, and whatever explanation we eventually come up with will rewrite parts of planetary science. But the flattened shape was just the beginning. As more images came in, processed through increasingly sophisticated algorithms designed to enhance subtle features, scientists began to see things on the surface that they couldn't immediately explain. There were bright spots, small patches of higher reflectivity scattered across the surface. There were dark streaks, possibly indicating exposed material from beneath the reddish tholin coating. And most curiously, there were what appeared to be small pits or depressions arranged in patterns that some researchers described as too regular to be entirely random. Now, the official position from NASA and the New Horizons team has always been cautious about interpreting these features. The resolution of the images, while extraordinary given the distance and the speed of the encounter, is still limited. The smallest features visible on Arakoth are roughly the size of a football field. Anything smaller is essentially invisible. So when researchers see patterns that look unusual, the standard scientific response is to acknowledge them, document them, and avoid speculating about their origins until more data is available, which, in this case, will never come. New Horizons is moving away from Arakoth at tremendous speed, and no other spacecraft is heading anywhere near that object. The images we have are the only images we'll ever get of that particular world. This is one of the reasons why some of what New Horizons saw has never been fully shared with the public in any detailed way. Not because there's some grand conspiracy, but because the data is ambiguous, the interpretations are uncertain, and scientists are reluctant to make claims they can't back up with definitive evidence. The detailed analysis papers, when they're published in journals like Science and Nature and the Astrophysical Journal, get read by a few thousand specialists worldwide. The general public sees the press releases, the polished images, the simplified narratives. The deeper anomalies, the things that puzzle the researchers themselves, tend to stay buried in technical literature where casual observers never encounter them. And that's a shame, because some of what's in those papers is genuinely fascinating. Consider, for example, the curious case of Arakoth's color variations. The overall surface is reddish, as I mentioned, due to the tholin coating. But certain regions are significantly redder than others, and the pattern of redness doesn't match what you'd expect from a uniformly bombarded surface. Some areas appear almost pristine, with relatively low levels of the reddish material, while others are saturated with it. The boundaries between these regions are sharp in some places, gradual in others. Why would a primitive, undisturbed object from the dawn of the solar system show this kind of variability? One hypothesis is that the surface composition isn't actually uniform. Different parts of the object might be made of slightly different materials that respond differently to cosmic radiation. Another hypothesis is that some kind of resurfacing has occurred, perhaps through outgassing or thermal cycling, exposing fresher material in some regions while leaving others to accumulate more tholins over time. Neither hypothesis is fully satisfying, and the data doesn't quite fit either model cleanly. There's also the matter of the neck. The narrow region where the two lobes of Arakoth meet shows some genuinely strange features. There's a bright collar of material around the neck, a band of higher reflectivity that suggests something different is happening there compared to the rest of the surface. Some researchers have suggested this material is finely grained dust or ice that has migrated to that region due to gravitational effects. The neck is the point of weakest gravity on the object, and over geological time, loose material could accumulate there, attracted by tiny but persistent forces. Other researchers have proposed that the bright collar represents exposed subsurface material, perhaps revealed by the original collision that joined the two lobes together. The collision was gentle, yes, but it still might have disturbed the surface enough to expose underlying ices. A third possibility is that the collar represents condensed volatiles, gases that occasionally sublimate from the interior and refreeze on the surface at this particular location. We simply don't know which explanation is correct, and we may never know. After Arakoth, New Horizons continued its journey deeper into the Kuiper belt. The spacecraft is now well beyond the orbit of even Arakoth, traveling toward the outer edge of the Kuiper belt and eventually into interstellar space, where it will join Voyager 1 and Voyager 2 as humanity's most distant ambassadors. But unlike the Voyagers, which are essentially in cruise mode at this point, with most of their instruments turned off to conserve power, New Horizons is still actively observing. Its instruments are still function, and it's still making measurements that nobody expected. One of the most remarkable findings from New Horizons in its extended mission has been a measurement that, at first glance, seems boring. The spacecraft has been measuring the background light of the universe, looking at the darkness between the stars. This is the kind of measurement that's almost impossible to make from Earth or from spacecraft closer to the Sun, because there's too much interference. Sunlight scattering off interplanetary dust, the so-called zodiacal light, fills the inner solar system with a faint but pervasive glow that obscures the true darkness of deep space. Earth's atmosphere adds its own scattered light. Even the moon contributes. To truly see how dark the universe is between the galaxies, you need to get away from all of that. And New Horizons, out beyond Pluto, beyond Arakoth, in a region of space where the zodiacal light is essentially gone, is in a perfect position to make that measurement. What the spacecraft found surprised everyone. The universe is brighter than it should be. Specifically, the diffuse background light in the visible and near-ultraviolet range is significantly higher than what can be accounted for by all the known sources of light, all the galaxies, all the stars, all the known structures in the cosmos. There's roughly twice as much light out there as theory predicts. This excess light has no obvious explanation. Some researchers have proposed that it might be coming from a previously undetected population of faint galaxies, dwarf galaxies too dim to see individually, but numerous enough collectively to contribute significant light. Others have suggested it could be from intergalactic stars, stars that have been ejected from their home galaxies and are now drifting alone through the vast, empty spaces between galaxies. There are also more exotic hypotheses, involving decaying dark matter particles or other unknown physical processes. None of these explanations is fully satisfying, and the puzzle of the excess background light remains unsolved. This is exactly the kind of finding that doesn't make headlines. It doesn't lend itself to dramatic press releases or stunning visual images. It's a number on a graph, a measurement that doesn't quite match a prediction, but it's potentially profound. If the universe is twice as bright as we thought, that means there's something out there we haven't accounted for. There's a source of light, or population of objects, that's been hiding in plain sight, contributing to the cosmic background, but undetected by our most powerful telescopes. New Horizons, by being in the right place at the right time, has revealed a gap in our understanding of the universe at the largest scales. And the implications of that gap are still being worked out. But there's another aspect of New Horizons' extended mission that's even more intriguing, and it has to do with what the spacecraft has detected, or perhaps almost detected, in the space immediately around it. The Kuiper belt isn't empty. It's filled with small objects, ranging in size from tiny dust grains to dwarf planets like Pluto. And as New Horizons travels through this region, it occasionally encounters this material. The spacecraft carries an instrument called the Student Dust Counter, designed and built by students at the University of Colorado Boulder. This instrument measures impacts from microscopic dust particles, recording each tiny collision as the spacecraft sweeps through space. By tallying up these impacts over time, researchers can estimate the density of dust in different regions of the Kuiper belt. And what they've found is that the dust density doesn't drop off the way models predicted it would. As New Horizons travels farther from the Sun, the amount of dust it encounters should decrease, because the Sun's gravity and radiation pressure both work to clear out the outer regions of the solar system. Far enough out, you'd expect the spacecraft to be essentially traveling through empty space, with only occasional dust impacts. Instead, the student dust counter is detecting significantly more dust than expected. The Kuiper belt extends farther and contains more material than current models suggest. This raises questions about the boundary between our solar system and interstellar space. Where does our cosmic neighborhood end? Where does deep space truly begin? The answer is less clear than textbooks have suggested for decades. Some researchers have begun to speculate that there might be a second, more distant belt of objects beyond the main Kuiper belt, a reservoir of icy bodies that we haven't directly observed, but whose presence is hinted at by the dust measurements from New Horizons. If such a structure exists, it would represent a significant addition to the architecture of our solar system. And it might explain certain other anomalies that astronomers have been puzzling over for years, including the strange orbits of certain distant objects that have led some researchers to propose the existence of a ninth planet far beyond Neptune. The hypothesis of a ninth planet, often called Planet 9 or Planet X, depending on which research group you ask, has been one of the most fascinating debates in modern astronomy. The idea isn't new. Astronomers have been speculating about undiscovered planets beyond Neptune for over a century. The original search for what eventually became Pluto was actually a hunt for a hypothetical Planet X, believed at the time to be perturbing the orbits of Uranus and Neptune. When Clyde Tombaugh found Pluto in 1930, it was initially thought to be that missing planet. But as we learned more about Pluto, it became clear that this small icy world was far too tiny to be responsible for the gravitational effects astronomers were trying to explain. The search continued. And in the past decade, that search has taken on new urgency because of patterns observed in the orbits of certain distant Kuiper belt objects. Patterns that some astronomers believe can only be explained by the gravitational influence of a large, undiscovered planet lurking in the outer darkness. The objects in question are called extreme trans-Neptunian objects, or ETNOs. They're a small subset of Kuiper belt objects with extremely elongated orbits that take them far beyond the main Kuiper belt, sometimes out to hundreds of astronomical units from the Sun. What's strange about them is that their orbits seem to be aligned in a particular direction. Statistically, this shouldn't happen by chance. The orbital orientations of these objects should be randomly distributed, but they're not. They're clustered, as if something massive is shepherding them, gravitationally herding them into a particular configuration. In 2016, astronomers Konstantin Batygin and Mike Brown at Caltech published a paper arguing that the only reasonable explanation for this orbital clustering was the presence of a massive planet, somewhere between 5 and 10 times the mass of Earth, in a highly elongated orbit far beyond Neptune. They predicted where this planet might be located and called for searches to find it. New Horizons fits into this story in a curious way. As the spacecraft travels deeper into the outer solar system, it provides a unique vantage point for studying the region where Planet 9, if it exists, might be located. The spacecraft's instruments can search for very faint sources of light, sources too dim to be seen easily from Earth-based telescopes. There's been speculation, never fully confirmed in public-facing communications from NASA, that the New Horizons team has been quietly using the spacecraft to look for hints of additional large bodies in the outer solar system. The data sets are vast, and the analysis is ongoing. Most of what the spacecraft sees, when it's not actively flying past a target like Arakoth, gets archived and processed gradually over months and years. Some of those archives might contain interesting signals that haven't yet been fully analyzed or publicly discussed. This isn't necessarily evidence of any kind of secret. Science moves slowly. Data analysis takes time. Peer review takes time. Confirming an extraordinary claim requires extraordinary evidence, and researchers are rightly cautious about announcing things they can't fully verify. But it does mean that there's potentially a gap between what New Horizons has observed and what the public has been told, not because anyone is hiding anything deliberately, but because the analysis simply hasn't been completed, or because the results are too ambiguous to share with confidence. And that gap is where some of the most interesting science happens, the slow, careful work of trying to understand observations that don't quite fit existing theories. One of the more provocative findings from New Horizons, and one that has received relatively little mainstream attention, involves a series of observations the spacecraft made in 2020 and 2021. During those years, the mission team conducted a campaign of parallax measurements, taking images of nearby stars from the spacecraft's position and comparing them to images of the same stars taken from Earth. Because New Horizons is so far away, billions of miles from Earth, it sees the stars from a very different angle than we do. This means nearby stars appear in slightly different positions when viewed from the spacecraft compared to viewing them from Earth. This shift, called parallax, is exactly the same phenomenon that lets you measure depth with your two eyes by comparing the slightly different views from each eye. By measuring parallax shifts of nearby stars from New Horizons' position, astronomers can directly measure the distances to those stars with unprecedented precision. The two stars chosen for these measurements were Proxima Centauri, the nearest star to our Sun, and Wolf 359, another close stellar neighbor. The images from New Horizons, when compared to simultaneous images taken from Earth, showed exactly the parallax shifts that theory predicted, confirming the distances to these stars and validating the method. This was the first time in history that interstellar distances had been measured using parallax with a baseline larger than Earth's orbit around the Sun. It was a remarkable scientific achievement. But what got less attention was what else was visible in those images. The deep space behind these nearby stars, the background of fainter, more distant stars and galaxies, was captured in unprecedented detail from a viewpoint nobody had ever had before. And some of what's in those background images has yet to be fully catalogued and analyzed. There are objects in those images, faint smudges and points of light, whose nature isn't immediately clear. Some are certainly known galaxies or distant stars. Others are harder to identify. The New Horizons team has been working through these images, comparing them to catalogues of known objects, trying to identify everything that's visible. Most of what they find is mundane, expected, already known. But occasionally something turns up that doesn't match any known object. These anomalies are usually attributed to image artifacts, cosmic ray hits on the detector, or simply objects too faint to have been previously catalogued. But the sheer volume of data means that some unusual features might not have been investigated thoroughly yet. This is the nature of deep space exploration. We send our spacecraft outward, they observe everything they can, and the data they send back is so vast and so detailed that human eyes can barely keep up. Algorithms help. Automated analysis pipelines can sift through gigabytes of data quickly, flagging features that might be interesting. But ultimately, real understanding requires humans to look at the results, interpret them, and decide what they mean. And there are far more interesting features in New Horizons data than there are researchers available to investigate them. Let me take you back to the Pluto flyby for a moment, because there's something about that encounter that's worth revisiting in light of what we now know about the broader mission. When New Horizons made its closest approach to Pluto in July 2015, the spacecraft used its instruments not just to study Pluto and Charon, but to map the entire vicinity. It looked for additional moons, for ring systems, for any debris that might pose a hazard to the spacecraft. The team was particularly worried about rings, because if New Horizons had hit even a small particle at 30,000 miles per hour, it would have been destroyed. The kinetic energy at those speeds is enormous. Even a grain of dust could punch through critical components and end the mission instantly. What they found around Pluto was unexpected. The Pluto system is more complex than anyone had predicted. In addition to Charon, the large moon discovered in 1978, Pluto has four smaller moons named Nix, Hydra, Kerberos, and Styx. These smaller moons were discovered between 2005 and 2012, and New Horizons photographed them all during its flyby. But the spacecraft also looked carefully for additional moons or ring material, using its sensitive cameras to scan the entire Pluto system. And while the public-facing summaries emphasized that no rings were detected, the more detailed analysis is more nuanced. There are hints of dust structures around Pluto, very thin and tenuous, that might represent the remnants of impacts on the smaller moons. When meteoroids hit the small moons, they kick up dust that temporarily orbits Pluto before being lost to space. New Horizons may have detected this dust in some of its images, though the signal is faint and the interpretation is uncertain. There were also some unusual features on Pluto itself that received less attention than they probably deserved. The famous heart-shaped feature, Tombaugh Regio, is composed of two distinct regions. The left side, the brighter and smoother part called Sputnik Planitia, is a vast plain of frozen nitrogen that shows clear evidence of being geologically young. There are no impact craters in Sputnik Planitia, which means the surface has been renewed recently in geological terms, probably within the last few 100,000 years. This is remarkable for a world as small and cold as Pluto. Most small bodies in the solar system have surfaces that are billions of years old, preserved relics of ancient bombardment. For Pluto to have such a young surface means that something is actively reshaping it, even today. The leading hypothesis is convection, slow churning motion in the nitrogen ice driven by heat from below. But the energy source for this convection is mysterious. Pluto is small, far from the Sun, and should have lost most of its internal heat long ago. Yet something is still warm enough to drive geological activity. Some researchers have proposed that Pluto might have a subsurface ocean of liquid water, kept warm by radioactive decay in its rocky core and insulated by its icy shell. If true, this would put Pluto in the same category as worlds like Europa and Enceladus, places where liquid water might harbor conditions suitable for life. The evidence for this subsurface ocean is indirect but compelling. The position of Sputnik Planitia on Pluto's surface, almost exactly opposite Charon in Pluto's tidally locked configuration, suggests that the basin contains a mass concentration that has gravitationally reoriented the entire dwarf planet. A liquid water ocean beneath the nitrogen ice could provide that mass concentration. If Pluto really does have an ocean, it will be the most distant ocean ever discovered, an underground sea sitting beneath frozen nitrogen plains on a world 3 billion miles from the Sun. And we'd never even suspect it existed if New Horizons hadn't flown by and given us our first close look. What other worlds out there might harbor similar hidden oceans, similar hidden possibilities? The Kuiper Belt is full of objects we've barely begun to study. The possibility of hidden oceans on small, distant worlds is one of the most exciting and unsettling implications of what New Horizons has revealed. For most of the history of planetary science, we assumed that liquid water required either proximity to a star, like Earth's situation, or strong tidal forces from a massive planet, like Europa's situation orbiting Jupiter. Pluto has neither. It sits in the cold outer darkness, far from any significant heat source, with no large planetary companion to flex it tidally. And yet there's compelling evidence that liquid water exists beneath its surface. If Pluto can have a hidden ocean, then potentially thousands of Kuiper Belt objects could harbor similar oceans. The outer solar system might be far more habitable, in the broadest sense of the word, than anyone previously imagined. And we have no way to know how many of these worlds exist without sending more spacecraft to investigate them, which we're not currently doing. But let's return to what New Horizons has been observing in the years since the Arakoth flyby, because that's where some of the most curious findings emerge. After Arakoth, the spacecraft entered what mission planners call its second extended mission phase. There are no more close flybys planned. The probability of another Kuiper Belt object lying directly in the spacecraft's path is essentially zero. The Kuiper Belt is vast, and the objects in it are far apart. Finding two suitable targets along the same trajectory was already an extraordinary stroke of luck. Finding a third would require either incredible fortune or significant fuel expenditure, and New Horizons doesn't have much fuel left. So the spacecraft now operates as a deep space observatory, using its remaining fuel only for the most essential maneuvers and focusing its instruments on distant observations. In this phase of the mission, New Horizons has been making measurements that don't require close encounters. It's been studying the heliosphere, the bubble of charged particles and magnetic fields that surrounds our solar system. It's been observing distant galaxies and stars from its unique vantage point. It's been measuring cosmic rays, those high-energy particles that bombard everything in space. And it's been continuing to monitor the dust environment in the outer solar system, with the student dust counter still recording impacts as the spacecraft sweeps through space. One of the more curious observations from this phase involves variability in the cosmic ray background. As New Horizons travels deeper into space, the cosmic ray flux it measures should increase. This is because the heliosphere partially shields the inner solar system from cosmic rays. The sun's magnetic field and the solar wind deflect a fraction of these high-energy particles, reducing how many reach the inner planets. As you travel outward, you move beyond more of this protection, and the cosmic ray flux increases. This expected trend has been observed. But what's been less expected is that the cosmic ray flux varies in ways that don't always correlate with solar activity. There are dips and spikes in the data that don't match patterns we see in solar wind measurements from other spacecraft. Some of these variations might be due to local conditions in the spacecraft's environment, like passing through regions where the magnetic field has unusual structure. Others might indicate something more interesting, perhaps the influence of nearby stellar processes, perhaps the effects of structures in interstellar space that we haven't fully mapped. This connects to a broader question that's become increasingly important in recent years, the question of what the boundary between our solar system and interstellar space actually looks like. For a long time, we treated the heliopause, the outer edge of the heliosphere, as a kind of sharp boundary. Inside the heliopause, you're in the solar system. Outside, you're in interstellar space. The Voyager spacecraft, which crossed this boundary in 2012 and 2018 respectively, gave us our first direct measurements of what conditions are like on either side. And what they found was that the boundary isn't sharp at all. It's complex, structured, dynamic. There are layers and waves and turbulent regions. The interaction between the solar wind and the interstellar medium creates phenomena that nobody fully predicted. New Horizons is following the Voyagers into this region, though it won't actually reach the heliopause for several decades. The spacecraft is currently in what scientists call the outer heliosphere, the region where the solar wind is slowing down as it approaches the boundary with interstellar space. And it's making measurements that complement what the Voyagers found, adding data points from a different trajectory and a different time period. The combined picture from all three spacecraft is starting to reveal an interstellar environment far more complex than anyone anticipated. Our solar system is moving through a region of the galaxy called the local interstellar cloud, a low-density region of hydrogen and helium gas. But within this cloud, there's structure. There are denser patches and sparser patches. There are regions with different magnetic field orientations. And our spacecraft, as they push outward, are essentially sailing through these structures, encountering different conditions as they go. What's interesting from a public communication perspective is that most people have no idea this is happening. The Voyager spacecraft are popularly described as having left the solar system, which is true in a particular technical sense, but misleading in another sense. They've crossed the heliopause, yes, but they're still very much inside what most astronomers would consider the broader sphere of solar influence. The Sun's gravity extends out to about 2 light-years, the distance where its gravitational pull becomes weaker than the gravitational pull of other nearby stars. The Voyagers and New Horizons are nowhere near that distance. They've barely begun to leave. And there are still presumably countless objects, comets, possibly even rogue planets, orbiting the Sun at distances far beyond anywhere our spacecraft will reach in the foreseeable future. The Oort cloud is one such region. It's a hypothetical spherical shell of icy bodies surrounding the Sun at distances ranging from about 2,000 to 200,000 astronomical units. That's vastly farther than the Kuiper belt. The Oort cloud, if it exists as theorized, contains trillions of icy bodies, the remnants of the early solar system that were scattered outward by gravitational interactions with the giant planets. We've never directly observed an Oort cloud object in its natural environment. The only Oort cloud objects we know about are the ones that get gravitationally perturbed and fall inward toward the Sun, becoming long-period comets. By the time we see them as comets in the inner solar system, they've left the Oort cloud behind. We've never seen this region directly. New Horizons won't reach it for thousands of years. The Oort cloud is essentially terra incognita for humanity, a vast region of our own solar system that we know must exist but can't directly study. And this is where the story of New Horizons connects to something even larger. The spacecraft is showing us, by its journey and its findings, just how much we don't know about our own cosmic backyard. We've sent probes to all the planets. We've landed on Mars and Venus and several moons. We've imaged Pluto and Arakoth. But these accomplishments, impressive as they are, represent only the tiniest fraction of what exists in our solar system. The Kuiper belt has hundreds of thousands of objects we've barely seen. The Oort cloud has trillions we've never seen at all. And beyond those, in the spaces between the stars, there are presumably more rogue worlds, more ancient remnants, more cosmic structures that we're only just beginning to suspect exist. Speaking of rogue worlds, this is another area where New Horizons has potentially relevant data, though again, much of it hasn't been fully analyzed or publicly discussed. Rogue planets are worlds that don't orbit any star. They drift through interstellar space, ejected from their original solar systems by gravitational interactions or formed independently from collapsing clouds of gas. Astronomers estimate that there might be more rogue planets in our galaxy than there are stars. Trillions of them, drifting through the dark. Most are far too dim to detect with conventional telescopes. They have no parent star to illuminate them. Their only light comes from residual heat from their formation, which is faint, and from the rare alignments where their gravity causes them to act as gravitational lenses, magnifying the light of more distant stars in ways we can detect from Earth. A spacecraft like New Horizons, traveling through space in a region with relatively little background light interference, could in principle detect rogue planets that pass close to its trajectory. The conditions would have to be just right. The rogue planet would have to be within a certain range of distances. It would have to be massive enough to have detectable heat, and it would have to pass through the spacecraft's field of view at a time when the cameras were observing the relevant region of sky. The probability of any individual rogue planet meeting all these criteria is extremely low. But over the course of New Horizons' multi-decade mission, with its instruments continuously gathering data, the cumulative probability of detecting something unusual isn't zero. There have been hints in the data, faint signals that some researchers have flagged as worth further investigation. None of them have been definitively identified as rogue planets, and the official position is that no such detections have been made. But the analysis is ongoing. There's also been speculation, more in the realm of educated guessing than confirmed science, that some of the unusual orbital patterns observed in distant Kuiper belt objects might be caused not by an undiscovered planet, but by a passing rogue planet, or even a passing star. Our solar system has been around for 4.5 billion years. In that time, it has presumably had numerous close encounters with other stars and possibly with rogue planets. Each encounter would gravitationally perturb the orbits of objects in the outer reaches of the solar system, leaving fingerprints that we might be able to read today by studying the orbital patterns of distant objects. The clustering of ETNOs that has been attributed to Planet 9 might alternatively be evidence of an ancient close encounter that we can't directly observe but whose effects persist in the architecture of the solar system. These are the kinds of mysteries that New Horizons is helping us understand, even if it's not designed specifically to solve them. The spacecraft is gathering data that contributes to our understanding of the outer solar system, and that data feeds into broader theoretical work being done by astronomers around the world. Let me bring you back to something specific now, because there's a particular set of observations from New Horizons that deserves closer examination. In 2017, while the spacecraft was in transit between Pluto and Arakoth, it conducted what mission scientists called a long-range reconnaissance campaign. The idea was to use the spacecraft's cameras to observe other Kuiper Belt objects from a distance. New Horizons couldn't visit these objects. They were too far off its trajectory, but it could photograph them from much closer than any Earth-based telescope ever could. This was a unique opportunity. From New Horizons' position deep in the Kuiper Belt, certain Kuiper Belt objects were only a few 100 million miles away, compared to the billions of miles they would be from Earth. The improved geometry meant New Horizons could measure their shapes, their rotation periods, their surface properties, and their satellites in ways that simply aren't possible from inside our own planet's orbit. The targets of this reconnaissance campaign included several Kuiper Belt objects with intriguing properties. There was a body called 2002 MS4, an object about 400 kilometers across, large enough to be considered a possible dwarf planet candidate. There was 2014 OS 393, smaller but interesting because of its unusual orbit. There were several others, ranging in size and characteristics. New Horizons photographed each of them from its position in space, capturing images that, while not as detailed as those from a close flyby, were still significantly better than anything possible from Earth. What the images revealed was, in some cases, surprising. Several of the Kuiper Belt objects observed by New Horizons appeared to have characteristics that didn't match expectations based on their distance and orbital properties. Their brightness varied in patterns that suggested complex shapes, possibly indicating contact binaries similar to Arakoth, or possibly indicating objects with multiple satellites that varied the total light output as they orbited. Some of the objects appeared to be redder than predicted, suggesting they too were coated in tholins like Arakoth. Others appeared to have unusual color distributions across their surfaces, with certain regions appearing significantly different from others. These observations, combined with what we learned from Pluto and Arakoth, are gradually building a picture of the Kuiper Belt as a far more diverse and complex region than was previously appreciated. But here's what's interesting about this data. The complete analysis of these long-range reconnaissance images is still ongoing. The team has published preliminary findings in conference presentations and a few peer-reviewed papers, but the full data set has not been comprehensively analyzed and reported. Some of the more unusual features in the images remain officially uncommented upon. There are objects in the field of view that haven't been definitively identified. There are color anomalies that haven't been fully explained. There are shape estimates that don't quite match predictions from theoretical models. This isn't because anyone is concealing the data. The images themselves are publicly available through NASA archives, but because thorough analysis requires resources and time that aren't always available for every dataset a spacecraft produces. Now, I want to address something that often comes up in discussions of NASA and what the agency does or doesn't share with the public. There's a popular conception that NASA hides discoveries from us, that there are vast archives of secret images and data showing things the agency doesn't want the public to know about. This conception is mostly wrong, but it contains a kernel of truth. NASA doesn't deliberately hide major discoveries. The agency is funded by taxpayer dollars and has a strong institutional commitment to public communication. Most data from NASA missions is made publicly available, often very quickly. The Planetary Data System, the archive where mission data is stored, is open to anyone who wants to download it. You can, right now, go online and access the raw images from New Horizons. You can process them yourself. You can look for things the official analysis might have missed. But here's the kernel of truth. NASA doesn't have the resources to fully analyze and publicize every observation made by every mission. The amount of data coming back from active spacecraft far exceeds the capacity of the agency's scientists to thoroughly examine. So inevitably, some observations get more attention than others. The flashy, public-facing discoveries get press releases and beautiful processed images. The more obscure or ambiguous observations get archived for future research. They're not hidden, but they're not actively highlighted either. And if you're not actively looking for them, you'd never know they exist. This is the practical reality of how modern space exploration works. The data is there. The conclusions are mostly there. But the synthesis, the storytelling, the connecting of dots, that's where things often fall short. Independent researchers, citizen scientists, and amateur astronomers have made significant contributions by going through archived NASA data and finding interesting features that the official mission teams missed or didn't emphasize. There are entire communities of people who spend their time processing raw images from New Horizons, Cassini, the Mars rovers, and other missions, looking for things that haven't been publicly discussed. Most of what they find is mundane or already known. Occasionally, they find something genuinely surprising. The story of New Horizons past Pluto is being written not just by the official mission team, but by this broader community of researchers and enthusiasts who are working through the data and finding new things to talk about. One particularly interesting line of independent analysis has focused on what some researchers call the void problem. As New Horizons looks back toward the inner solar system from its position deep in the Kuiper belt, it can image regions of the sky that look very different from how they appear from Earth. The background of stars is essentially the same, of course, but the foreground, the regions where solar system dust and gas would normally appear, is very different. From the inner solar system, the night sky is filled with subtle illumination from the zodiacal light that diffuse glow caused by sunlight scattering off interplanetary dust. From the outer solar system, where New Horizons is, this scattered light is much weaker. The result is a darker, cleaner view of the sky, allowing for more sensitive measurements of background light. What independent researchers have noted, going through New Horizons images, is that certain regions of the sky appear darker than expected even after accounting for all known sources of foreground and background illumination. There are patches of sky that show a deficit of light compared to neighboring regions, and this deficit isn't easily explained by known interstellar features or instrumental effects. These dark regions, sometimes called voids in this context, are statistically subtle. They might represent nothing more than random variations in the data, or they might represent genuine features of the universe, regions where something is absorbing or blocking background light, or regions where the cosmic structure is different from what we expect. The interpretations are debated. The data is intriguing but not definitive. There's another aspect of New Horizons' mission that deserves attention, and it concerns the spacecraft's interactions with its environment as it travels. New Horizons doesn't just observe its surroundings passively, it also affects them in subtle ways. The spacecraft has its own electromagnetic emissions, its own radio signals being broadcast back to Earth. It carries instruments that emit and detect particles. As it travels through space, it creates a small bubble of disturbance around itself, a microenvironment that's not quite identical to the surrounding interstellar conditions. This bubble is important because it affects how the spacecraft interacts with the dust and particles in its environment. Some researchers have noted that the patterns of dust impacts recorded by the student dust counter don't quite match what would be expected from a perfectly random distribution of dust in space. There are clusters and gaps in the impact record that might indicate the spacecraft is encountering dust structures, perhaps clumps of dust associated with specific Kuiper belt objects or regions, perhaps streams of dust from comet trails crossing the spacecraft's path. The interpretation is complicated, and the resolution of the measurements is limited, but the data suggests that the dust environment of the outer solar system is not uniform. It has structure. It varies. And mapping this structure could tell us important things about the dynamics of the Kuiper belt and the broader outer solar system. Connected to this is the question of what happens when New Horizons eventually crosses paths with the densest regions of the Kuiper belt. Most models suggest the spacecraft has already passed the densest concentration of objects. But as I mentioned earlier, the student dust counter is finding more dust than expected at every distance. If the Kuiper belt extends much further than current models suggest, then New Horizons might still encounter regions of higher density as it travels outward. The spacecraft is still in good health, and its instruments are still functional. But every additional year it operates, the risk of a damaging impact slowly increases. Eventually, statistically, something will hit it, or it will run out of power, or some other failure will end the mission. But until then, every day, New Horizons gathers more data and helps us refine our understanding of what's actually out there. There's one more thing about the post-Pluto phase of the mission that I want to discuss, because it ties into the broader theme of what New Horizons has revealed that hasn't been fully appreciated. The spacecraft has been imaging Pluto continuously, even after the flyby, from its receding position. These long-distance images show Pluto from angles and at phases that no other spacecraft has ever seen. They show how Pluto's appearance changes as the spacecraft's perspective changes, how different surface features become visible at different times. And crucially, they show changes in Pluto itself over time. The atmosphere has varied. The surface features have shifted slightly. The brightness of certain regions has changed in ways that suggest active processes are still occurring. Pluto, despite being 3 billion miles from the Sun, is a dynamic world. Its surface evolves. Its atmosphere expands and contracts as Pluto moves closer to and farther from the Sun in its highly elliptical orbit. New Horizons has captured glimpses of these changes, providing a time-lapse view of how a world at the edge of the solar system actually behaves over the course of years. The dynamic nature of Pluto's atmosphere is one of the most fascinating findings from the extended observations, and it reveals something profound about the nature of small icy worlds in the outer solar system. When New Horizons first approached Pluto in 2015, the spacecraft's atmospheric measurements showed that the dwarf planet had a thin but significant atmosphere of nitrogen, with traces of methane and carbon monoxide. The surface pressure was about 100,000 times less than Earth's, but it was real, and it was detectable. What surprised everyone was how the atmosphere extended much higher above Pluto's surface than predicted, reaching up to about 1,600 kilometers, more than twice as high as Pluto's radius itself. The atmosphere was leaking into space, with gas escaping Pluto's weak gravity and drifting away into the surrounding emptiness. This atmospheric loss has continued, and as New Horizons has watched from a distance, the dynamics have evolved. Pluto's orbit takes it from about 30 astronomical units from the Sun at its closest to about 49 astronomical units at its farthest. The dwarf planet passed its closest approach to the Sun in 1989 and has been moving outward ever since. As it moves farther from the Sun, the atmosphere should be cooling and condensing, freezing out onto the surface as nitrogen and methane ice. This is exactly what some models predicted would happen, but the actual observations have been more complicated than the predictions suggested. The atmosphere hasn't collapsed in the simple way that models forecast. It's persisted longer than expected, with surface pressure dropping more slowly than the cooling alone would explain. This suggests that something is keeping the atmosphere relatively warm and active even as the sunlight reaching Pluto decreases. The leading hypothesis involves Pluto's nitrogen ice plains, particularly Sputnik Planitia. The ice is dark enough to absorb significant amounts of sunlight, and the slow convection of the ice releases heat from deeper layers. This combination keeps the surface temperature higher than it would otherwise be, maintaining a more substantial atmosphere than pure thermodynamics would predict. The result is a world where the atmosphere and surface are coupled in complex feedback loops, with the surface controlling the atmosphere and the atmosphere shaping the surface through deposition and erosion of ices. New Horizons has been able to monitor these processes from its receding position, providing a longitudinal study of Pluto's atmospheric behavior that no other observation method can match. From Earth, Pluto appears as a featureless point of light. Only during rare stellar occultations, when Pluto passes in front of a background star, can ground-based telescopes measure anything about its atmosphere. New Horizons doesn't need occultations. It can observe Pluto directly, year after year, building up a record of how this strange world changes over time. The results have informed our understanding of how atmospheres behave on small bodies, with implications for our understanding of other dwarf planets, of Triton, Neptune's largest moon, which resembles Pluto in many ways, and of icy moons throughout the solar system. But let me bring you back to something I mentioned earlier, the question of what else New Horizons has photographed that hasn't received much public attention. There's a category of observations that the mission team has conducted that involves looking at distant regions of the sky, not towards specific targets, but in a survey mode. The cameras are pointed at large patches of sky, exposures are taken, and the resulting images are catalogued for future analysis. These survey observations are designed primarily to look for additional Kuiper belt objects that might be candidate targets for future encounters, or to detect any moving objects that might be of scientific interest. The data from these surveys is dense. Each image contains thousands of points of light, most of them background stars and galaxies. Identifying which points are actually solar system objects rather than background stars requires careful analysis, comparing images taken at different times to see which points have moved relative to the fixed stellar background. Solar system objects move because of their orbital motion. Background stars don't, at least not on time scales relevant to a spacecraft survey. By looking for points that change position from one image to the next, researchers can identify Kuiper belt objects in the data. This kind of analysis has identified hundreds of objects in the New Horizons survey images. Most of them are previously known Kuiper belt objects whose orbits had been determined by ground-based telescopes. The spacecraft's observations refined their positions and provided additional information about their properties. But some of the moving objects identified in the surveys don't match any known catalogue. They appear in the data, they move appropriately for solar system objects, but their orbits aren't well constrained because the spacecraft only observed them briefly and from a single vantage point. These objects exist, somewhere in the outer solar system, but their detailed properties remain unknown. They've been logged in mission databases, but haven't been the subject of dedicated follow-up observations. This is the slow accumulation of knowledge about the outer solar system. Each new object identified, even if its properties aren't fully understood, adds to our catalogue of what's out there. And as more objects are catalogued, patterns emerge. The distribution of objects in different orbital configurations tells us about the history of the solar system, about how planets migrated in the early days, about how the outer regions were shaped by gravitational dynamics over billions of years. New Horizons is contributing to this catalogue in ways that won't be fully appreciated for years, possibly decades, as researchers gradually work through the data. There's another aspect of the mission that I haven't yet discussed, and it concerns the spacecraft's optical communications experiment. New Horizons isn't equipped with optical communications hardware in the way that newer missions are. It uses radio waves for all its data transmission, the same general technology used since the dawn of the space age. But the spacecraft has been used for some experiments involving its imaging instruments and ground-based observers, looking at how lasers transmitted from Earth interact with the spacecraft's optical systems. These experiments are testing concepts that might eventually lead to optical communications between Earth and distant spacecraft, which would dramatically increase data transmission rates compared to current radio systems. The current data rate from New Horizons is painfully slow. As I mentioned earlier, It's comparable to a dial-up modem from the 1990s. Transmitting a single high-resolution image can take weeks. The complete data set from the Arakoth flyby took more than a year to download. This severely limits how much science can be done by any deep space mission. A future spacecraft equipped with optical communications could potentially transmit data thousands of times faster, opening up entirely new possibilities for exploration. The experiments being conducted with New Horizons are helping to lay the groundwork for these future capabilities, even though they don't directly produce new scientific findings about the outer solar system. Now, let me return to a topic that I think is genuinely fascinating: the way New Horizons has changed our understanding of how solar systems form. The observations of Arakoth, with its gentle two-lobe structure and pristine surface, have forced a reconsideration of planetary formation theory. The dominant theory before Arakoth was something called pebble accretion, where small grains of rock and ice gradually clump together under gravity, building up to larger and larger sizes through countless collisions. Over millions of years, these growing objects eventually become large enough to influence each other gravitationally, leading to a final phase where larger bodies collide and merge to form planets. Arakoth doesn't fit this picture cleanly. The object shows no signs of having been built up through countless violent collisions. Its surface is smooth, with relatively few impact craters considering its age. The two lobes came together gently, at very low velocity. This suggests that Arakoth and other small Kuiper belt objects might have formed through a different process, perhaps a process called streaming instability, where dense regions of dust in the early solar nebula gradually collapse under their own gravity, forming objects directly without the violent collision phase. If this is correct, it has profound implications for understanding how all planetary bodies form, not just in our solar system, but throughout the galaxy. The way planets come into being might be fundamentally different from what we thought. This insight, the gentle formation of Kuiper belt objects, is itself one of those things that hasn't been fully communicated to the broader public. The headlines from the Arakoth flyby focused on the strange shape, the snowman appearance, the reddish color. The deeper scientific implications, the way this small object has reshaped our understanding of planetary formation, has been largely confined to scientific journals and academic conferences. Most people who heard about Arakoth came away with the impression that it was a quirky little object that briefly captured the public imagination. They don't realize that it might represent a paradigm shift in planetary science, a clue to one of the most fundamental questions in cosmology. And this connects to a broader truth about space exploration that I want to highlight. The most important discoveries are often not the ones that make the biggest splash in the news. The flashy findings, the dramatic images of distant worlds, the discoveries of new moons or rings or unusual features, those are what get the headlines. But the truly transformative findings are often more subtle. They're patterns in data. They're refinements to theoretical models. They're new ways of thinking about old problems. These are the things that change science, but they don't translate easily into press releases. They emerge slowly, in conferences and seminars and review papers, building over years and decades into new understandings. New Horizons has produced many such subtle but important findings: the atmospheric dynamics of Pluto, the implications of Arakoth's structure for planetary formation, the unexpected density of dust in the outer solar system, the excess background light from beyond our galaxy. Each of these findings, on its own, might not seem like much, but collectively, they represent a substantial advance in our understanding of the outer solar system and beyond. And the spacecraft is still operating, still making measurements, still contributing to this slow accumulation of knowledge. There's also the question of what comes next for New Horizons, and what comes next for our exploration of the outer solar system more broadly. Will there be future missions to follow up on what New Horizons has found? The question of follow-up missions to the outer solar system is one of the most pressing issues in planetary science right now, and the answer is more complicated than most people realize. There's enormous scientific interest in returning to the Kuiper belt with more advanced spacecraft, capable of doing things New Horizons couldn't do. A return mission to Pluto, for example, could include an orbiter rather than just a flyby, allowing for sustained observation of the dwarf planet over years rather than just hours. An orbiter could map Pluto's entire surface, study its atmosphere through multiple seasonal cycles, and potentially deploy a lander to study the surface up close. The scientific value of such a mission would be immense. We'd learn things about Pluto and Charon that we can barely guess at from the limited data New Horizons collected during its brief encounter. But such missions are extraordinarily difficult and expensive. Reaching Pluto with a spacecraft heavy enough to carry the fuel and instruments needed for orbital insertion would require either a gravity assist trajectory through Jupiter, which is only available during specific launch windows, or the development of new propulsion technologies like nuclear electric propulsion. NASA has studied several concepts for return missions to Pluto over the years. None of them have been fully funded. The agency's priorities for outer solar system exploration have been focused on other targets, particularly the icy moons of Jupiter and Saturn, where the potential for finding life is considered higher than at Pluto. So while there are detailed mission concepts on the books for returning to Pluto and the Kuiper Belt, the actual development and launch of such missions remains uncertain. In the absence of dedicated return missions, the next best thing is to make the most of New Horizons while it's still operational. The spacecraft is expected to remain functional through at least the late 2030s, depending on power availability. Its plutonium-powered generator provides electricity, but the power output decreases gradually over time as the plutonium decays. Eventually, there won't be enough power to operate the instruments, and the mission will end. Until then, the team will continue to use the spacecraft for whatever observations are scientifically valuable. Long-distance imaging of Pluto, ongoing measurements of the heliosphere and cosmic rays, monitoring of the dust environment, and surveys of distant Kuiper Belt objects will all continue. The data will keep flowing back, slowly, year after year. There's also the possibility, though it's increasingly remote, of another close encounter. Mission planners continue to search for Kuiper Belt objects that might be reachable with the spacecraft's remaining fuel. The geometric constraints are severe. Any potential target has to lie almost exactly along New Horizons' current trajectory, because the spacecraft can only make small course corrections. The probability of finding a suitable object decreases as the spacecraft moves farther from the main Kuiper Belt. But searches continue, with telescopes including the Hubble Space Telescope and the James Webb Space Telescope occasionally being used to look for candidate objects in the relevant regions of sky. Beyond New Horizons, there are concepts for future missions that might dramatically expand our exploration of the outer solar system. One such concept is the Interstellar Probe, a proposed mission that would travel beyond the heliosphere and into true interstellar space, gathering data along the way about the outer solar system and the interstellar medium. The concept has been studied seriously by NASA, with mission designs that would allow the spacecraft to reach distances of several hundred astronomical units from the Sun. Such a mission could potentially detect Planet 9 if it exists, could map the heliosphere from outside, and could measure the interstellar medium directly without being inside the bubble of solar influence. The Interstellar Probe is currently in early study phases. Whether it will ever be built and launched depends on funding decisions that will be made over the coming decade. There are also concepts for missions specifically targeting outer solar system objects. The proposed Persephone mission would be a dedicated Pluto orbiter. The proposed Trident mission was designed to visit Triton, Neptune's largest moon. The proposed Centaur reconnaissance mission would visit one of the Centaurs, the icy bodies that orbit between Jupiter and Neptune and represent a transitional population between the Kuiper Belt and the inner solar system. Most of these missions are unfunded concepts at this point, but they represent the directions in which planetary science is interested in moving. Whether any of them get built depends on a complex set of factors, including political support, scientific priorities, technological readiness, and the always limited NASA budget. In the meantime, ground-based and space-based telescopes are doing what they can to study the outer solar system from a distance. The James Webb Space Telescope, with its infrared capabilities and high sensitivity, has been observing Pluto, Arakoth, and various other Kuiper belt objects in ways that complement New Horizons findings. JWST can detect cooler objects that are difficult to see in visible light. It can perform spectroscopy on Kuiper belt object surfaces, identifying the specific molecules present. It can search for new objects that haven't been catalogued yet. Each of these capabilities adds to our understanding of the outer solar system, even though no spacecraft is currently traveling to visit those objects. There's something I want to come back to, because I think it's important. When we talk about what New Horizons has seen past Pluto, we're really talking about the gradual revelation of how strange and complex our own solar system is. We grew up with diagrams of the solar system that showed the sun in the middle, the planets in their orbits, and maybe a vague indication of the asteroid belt and the comet cloud. That picture was simple and clean, and it gave the impression that we knew our cosmic neighborhood pretty well. New Horizons has helped reveal that this picture was woefully incomplete. Beyond Neptune lies a vast, complex, varied region populated by countless objects of every shape, size, and composition. The Kuiper belt is not a uniform field of debris. It's a dynamic environment with structure, with history, with secrets. And beyond the Kuiper belt lies the scattered disk, a population of objects on highly elongated orbits that can reach far beyond the main Kuiper belt. Beyond that lies the inner Oort cloud, then the outer Oort cloud, then finally interstellar space. Each of these regions has its own characteristics, its own population of objects, its own scientific mysteries. We've only directly visited a tiny fraction of even the closest of these regions. The rest remains unexplored, except through indirect observations from distant telescopes. Each region of the outer solar system that we eventually do explore in detail will probably surprise us, just as Pluto and Arakoth surprised us. We're still in the early days of understanding what's out there. There's another dimension to all this that I want to mention, and it concerns the cultural and philosophical impact of these discoveries. New Horizons has taught us that even objects that we thought we understood, like Pluto, can surprise us when we look at them closely. It has revealed that our solar system is more complex and more interesting than the simple models of our textbooks, and it has emphasized just how vast and varied the universe is. Pluto was, for most of the 20th century, a curiosity at best, a footnote in solar system astronomy. After New Horizons, it became a complex world with mountains and glaciers, and possibly an underground ocean. The transformation in how we see Pluto mirrors a broader transformation in how we see the outer solar system as a whole. From a vague, lightly populated region of mostly empty space, it has become a rich and structured domain that demands attention. This transformation has implications for how we think about humanity's place in the cosmos. The more we learn about our solar system, the more we realize how much we don't know. The galaxy contains hundreds of billions of stars, most of which presumably have their own planetary systems, their own Kuiper belts and Oort clouds, and assorted mysteries. If even our own solar system contains as much that we don't understand as New Horizons has revealed, the rest of the galaxy must be vastly stranger and more complex than we can currently imagine. The implications for the search for life elsewhere in the universe are profound. If small icy bodies in our outer solar system can harbor subsurface oceans, then the potential habitats for life are far more numerous than anyone previously thought. Let me bring you back to a specific question that I started this discussion with, the question of what NASA has and hasn't fully shared about New Horizons. I want to be precise about this, because I think it's important to distinguish between deliberate concealment, which I don't believe is happening, and the natural limitations of public communication about complex scientific data. NASA does share New Horizons data with the public. The major findings are reported in press releases and scientific papers. The data archive is freely available. Anyone who wants to dig into the raw data can do so. But there's a significant gap between the data being available and the data being interpreted, analyzed, and explained in ways that the general public can engage with. This gap is where the more interesting and ambiguous findings tend to live. The strange shape variations on Arakoth, the color anomalies, The unexpected dust density in the outer Kuiper belt, the excess background light, the hints of unusual features in survey images, the patterns that don't quite match theoretical predictions. All of this exists in the data, available to researchers who know where to look, but most of it never gets translated into accessible communications for the broader public. People who follow space exploration casually, watching documentary specials, or reading occasional news articles, mostly hear about the headline findings. They hear about Pluto's heart, about Arakoth's snowman shape, about the basic facts that fit into easy summaries. They don't usually hear about the more nuanced, more uncertain, more interpretively challenging findings. This is part of a broader pattern in science communication. Researchers, journalists, and institutions tend to emphasize findings that are clear, confirmed, and easy to explain. Findings that are ambiguous, controversial, or require lengthy explanation tend to get less attention. This isn't malicious. It's just how communication works. People have limited time and attention. So when people ask what New Horizons has seen past Pluto that NASA hasn't fully shared, the honest answer is that there's a lot of data and a lot of interpretive complexity that doesn't fit into the headline summaries. Some of it is genuinely puzzling. Some of it is interesting but ambiguous. Some of it is just slow to be analyzed because the resources for analysis are limited. None of it represents secret discoveries being deliberately concealed, but all of it represents knowledge that exists somewhere in the scientific community without being widely communicated to the broader public. Let me give you some specific examples of the kinds of things I'm talking about. There's an ongoing research program looking at how the dust impacts recorded by New Horizons' student dust counter relate to specific Kuiper belt objects. The idea is that some of the dust impacts the spacecraft has experienced might be associated with the cometary activity of particular bodies in the outer solar system. If a Kuiper belt object is outgassing, releasing material into space due to solar heating or internal processes, that material would form trails of dust that other objects passing through could encounter. Identifying which dust impacts are associated with which Kuiper belt objects could tell us important things about which objects are active and which are dormant. This research is ongoing. Some preliminary results have been published, but the comprehensive analysis is still years away from completion. And when it is completed, the findings are unlikely to make front-page news. They'll appear in specialized journals, be discussed at planetary science conferences, and gradually be incorporated into the broader understanding of the Kuiper belt. There's another ongoing analysis looking at the rotation periods and surface properties of Kuiper belt, objects observed by New Horizons during its long-range reconnaissance campaigns. By tracking how the brightness of these objects varies over time, researchers can determine their rotation rates. Some objects rotate quickly, completing a rotation in just a few hours. Others rotate slowly, taking days or weeks to make a single revolution. The distribution of rotation rates tells us about the history of collisions and gravitational interactions in the Kuiper belt. Fast-rotating objects might have been spun up by recent impacts. Slow-rotating objects might have been tidally locked by the gravity of a satellite or might have lost angular momentum through some other process. The data from New Horizons is helping to build this picture, but again, the full analysis takes years. There's also research being done on the colors of Kuiper belt objects, looking for patterns that might reveal information about their formation and history. Some objects are reddish, like Arakoth, while others are more grayish or even bluish. The colors correlate with orbital properties in complex ways that suggest the Kuiper belt is divided into distinct populations with different histories. Red objects might have formed in one region of the early solar system, while gray objects formed in another. The orbital evolution of the solar system would have then mixed these populations, but their colors preserve a memory of their origins. New Horizons has contributed important data to this research by observing several Kuiper belt objects in detail. The full picture is still emerging. There's something else I want to mention because it touches on one of the more provocative findings from the New Horizons mission. The spacecraft has, on rare occasions, been used to observe the inner solar system from its position deep in the Kuiper belt. Looking back toward the sun, the spacecraft can see the inner planets and their orbits in a way that no Earth-based observer can. In particular, New Horizons has imaged Uranus and Neptune from a distance, providing rare views of the ice giants from outside their orbits. These observations have been useful for studying the rotation and atmospheric properties of these planets, complementing data from other sources like Voyager and the Hubble Space Telescope. But there's been speculation, mostly in the realm of independent researchers and citizen scientists, that some of these observations might contain hints of features in the outer solar system that haven't been formally identified. When you look back from beyond Pluto toward the inner solar system, you're looking through a vast volume of space that contains countless objects. Some of those objects might be in alignments that produce unusual signals. Some might be detectable through their gravitational effects on background stars. Most of these speculations don't hold up under careful analysis, but a few have persisted in the discussions of researchers who work with the New Horizons archive. There are claims of unusual brightenings in certain regions of sky, claims of moving objects that haven't been catalogued, claims of patterns that might indicate previously unknown structures in the outer solar system. Most of these claims will probably turn out to be artifacts or misinterpretations, but the fact that they exist, that they're being discussed in the community of researchers who work with this data, suggests that the New Horizons archive contains material that hasn't been fully exhausted by official analyses. I want to talk about the heliosphere again, because this is one of the most scientifically rich areas where New Horizons is making contributions that aren't widely known. The heliosphere is the bubble of solar wind that surrounds our solar system. It's created by the constant outflow of charged particles from the sun, which pushes back against the interstellar medium and creates a kind of protective shell around everything within. The Voyager spacecraft showed us that this shell is complex and structured, with multiple layers and boundaries. New Horizons is now adding more data to our understanding of these structures. What's particularly interesting is that the heliosphere isn't stationary. It moves with the sun through interstellar space, and as it moves, it interacts with the surrounding interstellar medium in dynamic ways. The shape of the heliosphere isn't a simple sphere. It's elongated in the direction of motion, with a kind of bow shock in front and a tail behind, similar to how a comet has a coma and tail as it moves through space. New Horizons is in a position to study certain aspects of this structure that the Voyagers couldn't see, because the spacecraft is on a different trajectory and observing different regions. The data being gathered now will help complete our picture of how our solar system fits into its galactic environment. There's also a fascinating ongoing study of what happens at the boundary between the heliosphere and interstellar space. The Voyagers found that this boundary, called the heliopause, is more dynamic and complex than anyone predicted. There are turbulent regions where the solar wind interacts with the interstellar medium in unexpected ways. There are magnetic field structures that don't match theoretical predictions. There are signs of cosmic rays being deflected and shaped by the boundary in patterns that researchers are still trying to understand. New Horizons hasn't reached this boundary yet, but it's heading toward it. In a few decades, the spacecraft will cross the heliopause, providing a third data point along with Voyager 1 and Voyager 2. The comparison between the three crossings will help us understand how this boundary varies in different directions and how it changes over time. Let me bring you back to something more concrete, because I want to give you a sense of just how much data New Horizons has gathered and how much of it remains to be fully analyzed. Over the course of its mission, the spacecraft has transmitted multiple terabits of data back to Earth. That's an enormous amount of information, far more than any individual researcher could examine in a lifetime. The mission team has analyzed the highest priority data, the data directly related to the spacecraft's primary science goals. But there's much more in the archive that hasn't received detailed attention. Engineering data, calibration measurements, survey images, and various other categories of information all exist in the public archive, available for anyone who wants to dig into them. There are tools available for analyzing this data, but they require specialized skills and significant time investment. Researchers at universities and research institutions have access to these tools and skills, but they have to make choices about which data to prioritize for analysis. Other categories of data get archived and might or might not ever receive detailed examination. This is a common situation for major space missions. The Cassini mission to Saturn, for example, produced so much data during its 13 years at Saturn that researchers are still working through it years after the mission ended. The same will be true for New Horizons. The mission's data will continue to yield new findings for decades as researchers slowly work through the archive and apply new analysis techniques to old observations. This raises an interesting question about the nature of discovery in modern space exploration. When does a discovery actually happen? Is it when the data is collected by the spacecraft? Is it when the data is downloaded to Earth? Is it when the data is analyzed and a finding emerges? Is it when the finding is published in a peer-reviewed journal? Or is it when the finding is communicated to the broader public? The answer to this question affects how we think about what New Horizons has actually done. If discovery is collection, then the spacecraft has made countless discoveries, many of them sitting in archives waiting to be recognized. If discovery is publication, then the rate of discovery is slower and more constrained by the resources available for analysis and writing. If discovery is public communication, then the rate is even slower and more uneven. I think a reasonable answer is that discovery happens in stages, and each stage has its own characteristics. The data exists in the archives. Some of it has been analyzed. Some of the analyses have been published. Some of the publications have been popularized. The flow from raw data to public understanding is slow and lossy. Things get lost along the way, not deliberately, but simply because there's so much data and so few people to process it. This is why I say that some of what New Horizons has seen past Pluto hasn't been fully shared with the public. It's not that anyone is hiding things. It's that the process of moving findings from the data archive to the public consciousness is inherently limited, and a lot of interesting material falls through the cracks. There's one more thing I want to discuss before wrapping up this section, and it concerns the future of the New Horizons archive after the mission ends. When New Horizons eventually goes silent, when its power supply finally runs too low to operate the instruments and the radio, the mission will officially end. But the data it has gathered will live on indefinitely. The planetary data system maintains archives of all NASA mission data, and these archives are preserved with the expectation that they will be useful to researchers for decades or even centuries to come. New Horizons data will join the data from Pioneer, Voyager, and countless other missions in a vast repository of information about our solar system. Future researchers, equipped with new analysis tools and new theoretical frameworks, will be able to revisit this data and potentially find things that the original analyses missed. This has happened before. Data from the Pioneer missions, launched in the 1970s, is still being analyzed today by researchers using techniques that didn't exist when the missions were active. The Pioneer anomaly, an unexplained deceleration of the Pioneer spacecraft that was identified decades after the data was originally collected, became a major topic of study in physics before it was eventually attributed to thermal radiation effects. Voyager data continues to yield new findings as researchers apply modern analysis techniques to observations made in the 1980s. The same will be true for New Horizons. The discoveries from this mission are not just the ones being made now, but the ones that will be made in the future as our understanding of the outer solar system grows and new questions emerge that the existing data can help answer. There's a particular aspect of this future analysis that I find fascinating. Machine learning and artificial intelligence techniques are becoming increasingly powerful tools for analyzing scientific data. These techniques can find patterns in large datasets that human researchers might miss, can identify anomalies that don't fit standard models, and can correlate data across multiple sources in ways that would be impossible to do by hand. As these techniques mature, they will be applied to the New Horizons archive and to other space mission archives. The result will likely be a wave of new discoveries based on existing data, things that were always there in the observations, but that nobody had the tools to recognize. Some of this work is already beginning. Researchers are using neural networks to identify Kuiper belt objects in New Horizons survey images, looking for moving points of light that human observers might overlook. They're using statistical analysis to look for subtle correlations in the dust impact data, searching for signatures of specific objects or structures. They're applying advanced image processing to bring out features in Pluto and Arakoth observations that were too subtle to see in the original analyses. Each of these efforts has the potential to reveal new aspects of what New Horizons saw, even though no new data is being collected. There's something poetic about this idea that a spacecraft launched in 2006 might continue to make discoveries long after it has gone silent, simply through the application of new analysis techniques to its archived data. New Horizons will become a kind of fossil record of the outer solar system, preserved in digital form for future generations to study. The discoveries will continue to flow, slowly and quietly, for as long as researchers are interested in studying the data. In a real sense, the mission will never truly end. It will just transition from active observation to ongoing analysis. But while we wait for those future discoveries, there's plenty to think about in what New Horizons has already revealed. Let me try to summarize the broad implications of what we've learned from this remarkable mission. First, the outer solar system is much more dynamic and complex than anyone previously thought. Pluto is a geologically active world with possible subsurface oceans. Arakoth represents a previously unknown mode of planet formation. The Kuiper belt has more dust, more diversity, and more structure than predicted. These findings have transformed our understanding of what happens at the edge of our solar system. Second, our solar system is bigger and more populated than the simple textbook diagrams suggest. There are countless Kuiper belt objects, only a small fraction of which have been catalogued. There are probably more dust and small bodies than current models account for. There might be undiscovered planets lurking in the outer darkness. The Oort cloud, if it exists as theorized, contains trillions of objects that we've never observed directly. Our cosmic neighborhood is far more crowded than we used to think. Third, the boundary between our solar system and interstellar space is not a simple line. It's a complex region with multiple layers and dynamic interactions. New Horizons is helping us map this region in ways that complement the earlier work of the Voyager spacecraft. As we understand this boundary better, we're gaining insight into how our solar system fits into the galaxy, how it moves through space, how it interacts with the surrounding interstellar medium. Fourth, even objects we thought we understood can surprise us when we look at them closely. Pluto, before New Horizons, was a vague point of light that we thought of as a cold, dead world. After New Horizons, it became a complex world with mountains, glaciers, and possible oceans. The lesson here is that the universe is full of surprises waiting to be discovered, even in places that we've been observing for decades. We never really know what we don't know until we get close enough to look. Fifth, the slow pace of scientific discovery and communication means that there's often a significant gap between what has been observed and what is broadly understood. New Horizons has gathered an enormous amount of data, much of which is still being analyzed. The mission has produced findings that haven't yet been fully incorporated into mainstream understanding of the solar system. As more time passes and more researchers work with the data, more of these findings will emerge into broader awareness. But the process is slow. Now, let me address something that's been implicit throughout this discussion. There's a difference between scientific knowledge and public understanding, and the gap between them can be substantial. Scientific knowledge exists in journals, in conference proceedings, in datasets, in the minds of specialists who work in specific fields. Public understanding exists in news articles, documentaries, educational materials, and the general awareness of non-specialists. The flow from scientific knowledge to public understanding is mediated by science communicators, journalists, educators, and the institutions that produce and disseminate information about science. This mediation is imperfect. Some findings get amplified and reach wide audiences. Others get neglected and remain known only to specialists. When we ask what New Horizons has seen past Pluto that NASA hasn't fully shared with the public, we're really asking about this gap between scientific knowledge and public understanding. The data is there. The findings are being made, but the communication isn't reaching everyone. Some of the most interesting and important results from the mission are sitting in scientific papers that few people will ever read, in datasets that few people will ever examine, in conference talks that few people will ever attend. The information exists, but it's not flowing to the broader public in proportion to its importance. This isn't a problem unique to New Horizons. It's a general problem with how science is communicated in modern society. Major findings get reported, but most findings don't get widely communicated. The general public gets a curated version of scientific knowledge, filtered through choices made by editors, communicators, and institutions about what's worth publicizing. These choices are usually well-intentioned, but they inevitably leave a lot of interesting material out of the public conversation. People who want to know what's really happening in science have to dig deeper than the headlines, reading scientific papers, following specialized blogs, attending conferences, and engaging with the broader scientific community. For people interested in New Horizons specifically, there are resources available to learn more than what's in the typical news coverage. The mission's official website maintains detailed records of findings and observations. The planetary data system provides access to raw data for those who want to examine it themselves. Scientific journals publish detailed papers about the mission's findings, many of which are freely available through preprint servers or open access publications. There are amateur astronomy communities that follow the mission closely and discuss its findings in depth. For anyone who wants to know more about what New Horizons has actually seen, the information is accessible, but it requires effort to find and engage with. This brings me to a broader point about the relationship between space exploration and the public. New Horizons, like all NASA missions, exists in significant part because of public support. Taxpayers fund NASA, and NASA's missions depend on continued political and public backing. The agency has a responsibility to communicate with the public about what it's doing and what it's finding. And by and large, NASA does a good job of this. The agency produces beautiful images, engaging videos, accessible articles, and educational materials about its missions. But the limitations of public communication mean that even with the best efforts, only a fraction of what NASA actually does reaches the general public. What this means for New Horizons, specifically, is that the mission's full impact on our understanding of the solar system won't be fully appreciated for years. The findings being made now, the analyses being completed, the patterns being recognized in the data, will gradually be incorporated into textbooks, into popular accounts of solar system science, into the broader awareness of what we know about our cosmic neighborhood. But this incorporation takes time. The current generation of students will probably grow up with a much richer understanding of the outer solar system than their parents did, in part because of New Horizons. And future generations will grow up with even more refined understanding, as the mission's data continues to yield new findings and as additional missions add to our knowledge. So when we ask what New Horizons has seen past Pluto that NASA has never fully shared with the public, the honest answer is complex. There's a lot of data that hasn't been fully analyzed. There are findings that haven't been widely communicated. There are mysteries that remain unsolved. There are anomalies that nobody fully understands. And there's the simple reality that even the best science communication can't convey everything that a major space mission discovers. The story of New Horizons is still being written, both in terms of what the spacecraft continues to observe and in terms of how researchers interpret what it has already shown us. The final chapter of this story is in some ways the most important because it's about what comes next. New Horizons is still out there. Right now, as you're reading this, the spacecraft is somewhere beyond the orbit of Arakoth, traveling at tens of thousands of miles per hour into regions of space that no human-made object has ever visited at this particular location. It's gathering data, sending signals back to Earth, contributing to our understanding of the outer solar system, and it will continue to do so for years to come. until its power finally runs out and it goes silent. When that day comes, sometime in the late 2030s, or perhaps a bit beyond, New Horizons will join the Pioneer and Voyager spacecraft as a silent Voyager carrying humanity's presence into the depths of interstellar space. The spacecraft won't crash into anything. It won't be retrieved. It will simply keep moving, propelled by its initial velocity and the slow influence of gravity, traveling outward through the Oort cloud and eventually into the broader galaxy. It carries no message or recording specifically designed for extraterrestrial recipients, unlike the Voyager Golden Records. But it does carry a small commemorative plaque, a CD-ROM containing the names of supporters and team members, a portion of the ashes of Clyde Tombaugh, who discovered Pluto, and various other mementos that connect this small spacecraft to the human civilization that built and launched it. In hundreds of thousands of years, New Horizons will pass close to other stars, though never close enough to be captured by their gravity. It will continue drifting through the galaxy for hundreds of millions or perhaps billions of years, slowly accumulating cosmic ray damage and gradually being eroded by interstellar dust. Eventually, on time scales we can barely comprehend, it will be destroyed by these processes or by some chance encounter with a larger body. But for vast stretches of time before that happens, it will remain intact, a fossil of early 21st century human technology carrying our species' presence into the depths of the galaxy. That's a remarkable thing to think about. A spacecraft built in laboratories in Maryland and California, launched from Florida, controlled by people in offices and command centers across the country, will outlast all of us. It will outlast our civilization. It will outlast our species, almost certainly. It will continue to exist as a physical object long after every memory of why it was built has been lost. Whoever or whatever might eventually find it, in some unimaginably distant future, will encounter a relic from a forgotten age of cosmic exploration. The mission's discoveries about Pluto and Arakoth and the Kuiper Belt and the cosmic background light might be incorporated into the knowledge of future civilizations, or they might be lost forever. But the physical spacecraft, traveling through the galaxy at its constant velocity, will persist. This is why the question of what New Horizons has seen and what we've fully understood from its observations matters so much. The spacecraft has given us a glimpse of regions we may never visit again. The data it has gathered represents the only detailed information we have about Pluto and Arakoth, and probably the only detailed information we'll ever have. If we don't fully analyze and understand what New Horizons has shown us, those insights will be lost. Future generations might have to launch new missions to gather the same kinds of observations, missions that won't happen for decades if they happen at all. The information in the New Horizons archive is irreplaceable, and the responsibility for extracting maximum value from it falls on the researchers and institutions working with the data today. But there's also a broader responsibility, one that falls on all of us who care about space exploration. We need to support the kind of science communication that goes beyond headlines and gets into the deeper, more interesting, more ambiguous findings that missions like New Horizons produce. We need to be patient with science, allowing it the time it needs to fully analyze data and develop understanding. And we need to be curious enough to dig deeper than the surface-level stories, to seek out the more complete picture of what we're actually learning about our cosmic neighborhood. When I started this discussion, I asked what New Horizons saw past Pluto that NASA has never fully shared with the public. The answer, I hope you now understand, isn't a list of hidden discoveries or suppressed images. It's a more nuanced and more interesting story about how scientific knowledge is created, communicated, and understood. New Horizons has seen many remarkable things. Some of them have made headlines. Others have been discussed in scientific papers but never reached broader audiences. Others remain to be fully analyzed and recognized. The mission's full impact on our understanding of the outer solar system won't be appreciated for years, possibly decades. And by the time it is fully appreciated, the spacecraft itself will probably be silent, drifting through interstellar space, carrying its archive of memories from an era of exploration. What I find most beautiful about the story of New Horizons is the way it reveals how much we don't know. Before the mission, we had vague ideas about Pluto and the Kuiper belt. We had theoretical models that predicted what we might find. We had telescope observations that hinted at certain properties. But we didn't actually know. We hadn't been there. We hadn't seen for ourselves. When New Horizons arrived at Pluto and showed us what was really there, the answer was far stranger and more interesting than anyone predicted. The same was true at Arakoth, and it will probably be true at every other object in the outer solar system that we eventually visit. The universe is consistently more surprising than our best models suggest. The lesson of New Horizons is that we should expect this. We should expect to be surprised. We should look forward to having our assumptions overturned. This is what makes space exploration so important and so worthwhile. We send spacecraft to distant places not just to confirm what we already believe, but to learn what we don't yet know. Every mission to a new world has the potential to revolutionize our understanding of that world, and by extension, of all similar worlds throughout the cosmos. New Horizons did this for Pluto and the Kuiper belt. Future missions will do it for other regions of space, and each new mission will reveal more of the gap between our current understanding and the actual reality of the universe. There's a famous quote attributed to various people, often paraphrased as the universe is not only stranger than we imagine, it's stranger than we can imagine. New Horizons is one of many missions that have demonstrated the truth of this idea. Pluto, before New Horizons, was a fuzzy point of light that we thought we understood at a basic level. Now we know that what we thought we understood was almost entirely wrong. The real Pluto, the one revealed by New Horizons, is far more complex and dynamic than the simple cold rock we used to imagine. The same is undoubtedly true of countless other worlds we haven't yet visited. This is why the search will continue. This is why missions like the proposed interstellar probe, or potential return missions to Pluto, or new explorations of the Kuiper belt and beyond, are so important. We have a vast solar system to explore, and we've only just begun. New Horizons has shown us how much more there is to learn. The next missions will show us more, and the missions after that will show us more still. The story of solar system exploration is just getting started, and we're privileged to live in the era when humanity is actively pushing back the boundaries of the unknown. The vanishing observations, the unexplained patterns, the anomalies in the data, the parts of the New Horizons archive that haven't been fully analyzed, all of these are reminders that science is an ongoing process. We don't reach definitive understanding through a single mission or a single observation. We accumulate evidence over time, debate interpretations, develop new theories, test those theories with new observations. Sometimes we get things right on the first try. Sometimes we have to revise our understanding multiple times as new evidence emerges. New Horizons is contributing to this process in important ways, and that contribution will continue for as long as researchers work with its data. So the next time you look up at the night sky and try to imagine the outer solar system, think about what's really out there. Think about the icy plains of Pluto with their slow convection and possible subsurface ocean. Think about the gentle two-lobed shape of Arakoth, preserved from the dawn of the solar system. Think about the countless other Kuiper belt objects, most of which we haven't seen, but which exist in a region of complexity and diversity that we're only beginning to appreciate. Think about the heliosphere with its dynamic boundary, about the cosmic background light that's brighter than it should be, about the dust in the outer solar system that's more abundant than predicted. All of these things are real. All of them are out there right now. And New Horizons, that small spacecraft no bigger than a piano, is still helping us understand them. The mission is still going. The data is still flowing. The discoveries are still being made. Some of them will reach the headlines. Some won't. But all of them are contributing to our slowly growing picture of the cosmic neighborhood we live in. Thank you for joining me on this journey through what New Horizons has revealed about the regions past Pluto. The story isn't over. It will continue for as long as the spacecraft operates, and for years afterward as researchers work through its data. New discoveries are coming. New mysteries are being uncovered. New understandings are emerging. And we, the curious observers, get to watch it all unfold in real time. That's a remarkable thing to be part of. and I hope this discussion has given you a richer appreciation for the depth and complexity of what we're learning about our solar system. If you've enjoyed this exploration of one of the most fascinating missions in modern space science, take a moment to like the video, share it with someone who might appreciate it, and subscribe to the channel for more deep dives into the mysteries of the cosmos. Leave a comment below telling me what you think New Horizons might still discover before the mission ends, or what other space missions you'd like to learn more about. Your support helps this channel reach more curious minds, and your engagement makes these explorations possible. Good night, and keep looking up at the stars, wondering what's out there waiting to be discovered, what's hidden in the data, and what mysteries the next generation of explorers will help us unravel.